The title of this presentation is a city-based climate service. We will go through some of the main components and processes of the Urban Multi-Scale Environmental Predictor. Prepared as a common tool for planners, researchers, and practitioners, UMEP is an important tool for climate mitigation in urban scenarios. It is described as an integrated tool for urban climatology and climate-sensitive planning applications. Data for more complex models may be imported into UMEP, such as building heights, materials and their spatial arrangement, land cover types, meteorological data, and remote sensing data. Alternatively, the outputs from each several models can also be exported to other more complex modeling systems in weather, climate, hydrology, and environment. There are several main modules in UMEP. The name of Extreme Finder is self-explanatory. This module is used to identify heat waves and cold waves. Surface Urban Energy and Water Balance Scheme, or SUEWS, is an urban land surface model. The model simulates the urban radiation, energy and water balances using commonly measured meteorological variables and information about the surface cover. It is used to understand urban energy and water balance, which is a precondition to extreme weathers. It can also be used to understand green infrastructure on runoff. Solar and long-wave environmental irradiance geometry model is used to identify potential hazard areas, potential sites for outdoor activities. Solar energy on building envelopes model estimates short-wave irradiance on ground, roofs, and building walls based on high-resolution digital surface models and input meteorological forcing data. QF is the anthropogenic heat, a model to estimate human-generated heat, such as those from traffic, metabolic, and building emissions. There are two implementations. One provides simple estimates at low spatial resolution, and another one produces high-resolution estimates with greater insights into specific types of energy use. In Tables 1 and 2 of Lindbergh's 2018 paper, you will find detailed description of each module, their parameters, applications, and outputs. Next, we will have a brief look on some of these modules. The first, we look at Extreme Finder. This module provides 4 methods to identify heat waves and 3 for cold waves. Different percentiles from meteorological time series are used to define extremes. Daily values are then evaluated to determine if the extreme event has occurred. In Figure 2, Extreme Finder identifies the days and the maximum, average or minimum of daily temperatures for all extreme highs and lows during the period of interest. The x-axis represents the date of the year from January to December. The y-axis shows the period of interest from 1990 to 2008. The colored boxes in yellow and red show the daily maximums labeled as extremes. For the understanding of energy and water balance fluxes, which are critical to surface-atmosphere interaction in an urban area, we have the Surface Urban Energy and Water Balance Scheme model. It uses an evaporation interception approach for an area comprises of 7 land cover types, namely water, buildings, grass, paved, bare soil, deciduous trees and shrubs, and evergreen trees and shrubs. The urban energy and water balance varies with different neighborhood or local scale characteristics. These urban environmental characteristics affect the impact of extreme conditions like heat waves, droughts, floods, etc. The stage of each surface type at each time step is calculated from the running water balance of the canopy, where the evaporation is calculated from the Penman-Menthie equation. The soil moisture below each surface type but excluding water is considered. This chart shows the workflow of running the model. The first column shows pre-processing. The second column shows all the data inputs, digital surface model of vegetated area and built-up land, population densities, land cover type, and meteorological data. One important element is local climate zones, which is connected to our previous lessons. After all the inputs are ready, the module will calculate morphometrics from local climate zones and land cover fraction. We will describe the data output in the next slides. Here we show the data input. Figure A is the land cover overlaid with a polygon grid. Figure B is digital surface models and canopy digital surface model derived from an airborne LiDAR dataset. These data were obtained in the summers of 2005 and 2008. Figure C is population density. Population information can be generated based on the polygon grid through QGIS2 zonal statistics. This zonal statistics tool has been practiced in Practical 2. The figures A, B, and C show the simulation results in London, United Kingdom, from 17th of July to 27th of October in 2015. Figure A is the average daytime sensible heat flux. Figure B is the time series of net radiation for grid ID 44. The red represents sensible heat. The black represents net radiation. Figure C is the scatter plot between hourly values of Q star and QH grid ID 44. The figures D, E, and F show results of Helsinki, September and November 2010. Figure D is an aerial image of the water monitoring area, and Figure E represents land cover fractions derived from LiDAR, and Figure F is the scatter plot between surface runoff and precipitation for different planning scenarios. Base run is the current case, and different scenarios are simulated if there are 10 or 30% more street trees and grass areas. Next, we want to talk about temperature. First is the mean radiant temperature. It is the most important variables to understand outdoor comfort. We can use the solar and long-wave environmental irradiance geometry model to calculate mean radiant temperature. Input variables include the 3D vegetation covers and variation in ground cover. This figure describes the spatial input and output data. Inputs include A. Digital surface models, B. Ground cover, and UMEP-derived data such as C. Sky view factor from buildings and vegetation, D. Wall pixels and heights. The pixel resolution here is 1 meter. The mean radiant temperature results is calculated for Gutenberg, 26 July 2006. Figure E shows the result at 1 p.m. Figure F shows the hourly mean radiant temperature and the air temperature for the courtyard point of interest. The point of interest can be represented as a point vector layer. This figure shows another example of the Civic Square, Mapogapastan, in Stockholm, Sweden. Figure A is the mean radiant temperature at 2 p.m. from a hot summer day, 28th of July, 1994. And Figure B is a hazard map based on the number of hours when the mean radiant temperature is higher than 59.4 degrees Celsius on one day. Figure C is the same as Figure B, but with a 2 degrees Celsius increase in air temperature, and Figure D with 4 degrees Celsius increase in air temperature. The hazard maps shows the increased multitudes in hazard area and their spatial distributions. The solar energy on building envelopes module calculates irradiances or incoming radiation at pixel level on building roofs and walls using a 2.5-dimensional model. The contrast between sunlit and shaded surfaces can explain micro-scale differences in urban climate. For example, the spatial variation in road surface temperatures. The solar energy on building envelopes model calculates the sunlit fraction using high-resolution DSMs and shadow calculator. This figure shows the result of the rooftop irradiance in central Uppsala, Sweden. Figure A is the statistics for one of the buildings. Figure B is the 3D view of short-wave irradiance on walls and rooftops. Anthropogenic heat flux is the heat released directly by humans and their activities. It is a distinct feature of urban areas. In UMEP, anthropogenic heat flux can be modeled using two stand-alone approaches. The first methodology uses the Lucy methodologies described in Allen's 2012 paper. It provides simple estimates at low spatial resolution. The second method is a re-implementation of the method described in Nimerino's 2011 paper. It produces high-resolution estimates with greater insights into specific types of energy use. This figure is an example of Greater London in October 2015. The input data is population density. The figures B, D, F to the right show larger anthropogenic heat towards the city center. The spatial scales are limited to 1 kilometer. At spatial scales less than 1 kilometer, movements of people, for example, from home to work, are important, and the structure of the road network needs to be captured. Example output maps are shown in figures A, C, and E. Because road network topology is used, the result is a notably different spatial structure in figures C and D. If we compare figures E and F, we can see a strong enhancement in the center of the city. This shows the effect of using the workday rather than residential population on the daytime metabolic emission. A similar enhancement is also evident in the building emissions if we compare figures A and B. This is attributed to the use of spatially resolved energy consumption compared with residential population-based attribution. To recap, the City-Based Climate Service 2 Urban Multi-Scale Environmental Predictor is introduced through a series of applications. The QGIS plugin has a coupled model system of state-of-the-art 1D and 2D models, which can provide estimates of essential urban climate processes. It also provides tools for determining parameters for more complex 3D models. For references, please refer to the Lindbergh 2018 paper. Here we have listed some essential information on using the UMEP software.